אוקיי, רק לפני שניכנס, אז באמת מי שלא מכיר, אז יש את הדף של יום הסדנאות באתר של הכנס, נשים את הלינק בצ'אט למי שירצה. דקה אחת. ופה בעצם יש את כל המידע לגבי כל ההרצאות, כל סדר היום, כל מה שצריך, שמות המרצים, פרטים, עניינים וכולי. אני רק אתחיל בהצגה בעצם של הדובר הראשון שלנו, דוקטור ניר רגב, ואני אתן לו עוד כמה דקות במקום לגנוב לו מההצגה עצמה, ואחר כך ניר, אתה תרגיש חופשי להציג ולהוסיף כמה שתרצה מהרקע שלך בארץ וכולי. אז אני אציג את ניר. דוקטור ניר רגב is an expert in AI and radar signal processing, specializing in FMCW and pulse Doppler radars. His work focuses on the development of algorithms for target detection and tracking in MATLAB, Python, and C++. Dr. Regev has a deep background in statistical signal processing and applies his expertise to both radar and computer vision technologies and their intersection with artificial intelligence. He is proficient in various AI domains, including generative AI and deep learning for semantic segmentation. Dr. Regev is the founder of AlphaZero AI and serves as an adjunct professor in electrical and computer engineering at Cal Poly, the California Polytechnical Institute at Pomona campus. With a strong record in both academia and industry, Dr. Regev leads projects that bridge theoretical research and practical application, enhancing real-time technology solutions. Dr. Regev holds a PhD, Master of Science and Bachelor of Science in Electrical Engineering from our very own אוניברסיטת בן גוריון, וניר, אני מניח שירצה לספר אחר כך קצת על הרקע שלו, ואנחנו מאוד שמחים שיצא לנו ככה להביא אותך ולשלב אותך פה ביום הזה. אני לא יודע, אם אתה מעדיף לדבר באנגלית או בעברית, זה כמובן לשיקולך המלא. וזהו, אני חושב שאנחנו ניתן לך את הבמה, וככה תוכל להתחיל עוד איזה דקה-שתיים לפני שאנחנו מתניעים.
אוקיי, גרייט.
הבמה שלך, ניר.
על הכיפק, תודה רבה, יניב. רק תיקון קטן, השם של החברה שלי, as we will see, is א' זירו. זה האות א'.
זירו. א'.
לא אלפא, א'. א' זירו זה גם מושג מתמטי, זה מספר קנטור, אבל גם רצינו לשים את האות א' ב' העברי שמה, אז זה א', תן לי לנסות לשתף פה מסך. This will stop other screen sharing, yes? אוקיי. עכשיו אני הולך להציג את המצגת הזאת. כולם פה דוברי עברית? או כולם מבינים עברית? או שאני צריך לדבר גם באנגלית, יניב?
I'm sorry, I'm לא מדבר עברית, אנגלית, it's possible, okay. It's very interesting. Thank you.
All right, so let's switch to English. I'll probably throw in a couple of words in Hebrew, but the majority of the presentation, I'll do it in English. You guys can hear me fine? You can see my screen?
שומעים אותך היטב, we can see you, we can hear you, everything is awesome.
Okay, perfect, great. All right, so let's start. The title of this presentation is AI-driven system design for advanced radar technology. I think the key message that I want to convey out is that leveraging AI can unlock new frontiers in radar systems and radar system design and optimization. This presentation will explore new AI's paradigms that can be applied to radar systems, radar system design, to drive innovation and performance improvement in radar. We'll cover the core capabilities of AI that makes it a powerful tool, and we'll showcase some real-world examples of how AI-driven radar systems are delivering breakthrough results in the industry and not only in academia. Some words about me. I'm the founder of AlphaZero, The website is aleph0.ai. It's a leading AI technology company. We specialize in radar and lidars and computer vision. And we develop cutting-edge AI solutions for a range of industries. Amongst our customers, you can find Google, ResMed, Ecodyne, John Deere, and many others. And as you can see, from the Googles to John Deere's, there is like a whole spectrum of industries. We're probably everywhere there. ResMed is a medical device company. Ecodyne is a radar company. Google is Google. John Deere is a utility type manufacturing company. So we're everywhere when there is a need, when there is needs for either sensing with sensors like cameras, lidars, and computer vision. So my background, I started back in 1998 working on this tank, the Israeli Merkava, and all of my customers and the lectures that I do online, students, they all see this tank and my Israeli hat. And if they have a problem with it, they don't work with me. In addition to my work, I'm also an adjunct professor in California State Polytechnic University in Pomona, in the electrical engineering department. I teach courses mainly, and I have a large community of students that has joined. It's managed on Discord, and they joined, and they get mentorship from industry professionals that I enlist for the cause. Okay? I also maintain my personal website. It's drnirregev.com, in which I maintain tutorials, papers, articles, videos of lectures, courses that I teach, and so on and so forth. Let's start with the presentation. Now, please, if you have any questions, just ask during the presentation. Okay, let's try to keep it, at least from my point of view, as informal as possible. Okay, so radar systems are critical for many applications, from defense to air traffic to weather monitoring. I deployed radar systems for aerospace defense type applications, for inside the house, like baby monitoring and elderly care, to outside the house with applications like security applications, to inside the car, like monitoring the amount of passengers, the state of the driver, the forgotten baby in the car syndrome prevention, and outside the car for autonomous driving. We all know that. The key components, I guess, in a system level of a radar system are the antenna RF and RF front end, and there is then the signal processing block that encompass usually a detector, a tracker, and a target classifier. Okay, the signal processing part of the radar chain is the one that is taking the sampled raw sensor data and extracts everything we can tell about what's going on in the environment, from the XYZ coordinates of targets, their radar cross-section or energy they emit, the return to the polarization and the Doppler of the target, up to the tracking apparatus or the tracking module of this radar signal processor that tracks targets in a 3D space and maintain information about them. And if we go up a level, we have the classifier, which is to say which target is it? Is it a drone? Is it a missile, ballistic missile? Is it a bird that we don't care about? Is it a human that is trying to cross the border, and so on and so forth? There is also a layer, sometimes, there is not all the time, but sometimes there is a layer of fusion that correlates and fuse either more radar sensors together or radar, lidar, and cameras together, and over time managing the multiple targets they produce. Finally, each of these components plays a vital role in creating an effective and a capable radar system. So some challenges in traditional radar system design. So we face significant design challenges that make designing a radar complex and difficult. Capturing the real world dynamics of targets and the behaviors of a radar system is extremely complex, requiring an extensive modeling and simulation phase at any given project. When I work with customers and when I worked for companies back in the day, we always started with simulations. The design process involves many iterative cycles of testing, refinement, which is time consuming and also resource intensive. It's not just one person, it's departments of persons working on this. It involves working in the lab, it involves working with manufacturers and so on and so forth. Manually, like day-to-day type of tuning and optimizing parameters in radar and configuration of waveforms in radar is a tedious and error-prone task for humans. These challenges make traditional radar design complex and a very involved task, if you will, highlighting the need for more efficient and streamlined approaches. So what can we do with AI? AI can optimize radar design through automated parameter tuning and multi-objective optimization, allowing us to find the best configurations, if it's for an antenna array or for a waveform parameters like bandwidth and chip duration or pulse duration, if it's for novel other type of phase-coded waveforms. We will see examples in this presentation. We all in the radar industry can benefit from a more holistic type of AI that will at least advance us towards what we want to achieve. So I think my message here is that AI can significantly accelerate the radar design cycle, allowing for rapid iterations and faster time to deployment. The visualization we will dive into visualization of a sample of AI algorithms that I prepared as a demo for this presentation. But for now, this is the benefits that the industry as well as the literature covered by both industry and academia are bringing forth. All right, so AI-based design methodologies are becoming increasingly important in engineering and product development, and not just in radar. I wanted to provide an overview of some key AI-based techniques that we can leverage in radar. So first, I call it aided system or AI DED, or the short of AI aided system, that use AI to automate aspects of the design process. Next, machine learning techniques like neural networks can be used to model complex systems and optimize performance of systems. And we will dive into examples in this presentation. Generative design leverages evolutionary algorithms and discriminated generator type algorithms to explore design spaces and generate novel concepts. And again, why concepts? It can be either a new waveform that we haven't seen before, or a new design for an antenna array that we've never seen before that optimize some criteria. Finally, meta learning approaches like transfer learning can accelerate design process by applying the knowledge gained from one radar down to another radar or another task. These AI-based methods offer the potential to make design more efficient, innovative, and data-driven. Okay, so again, the key focus of this slide is the AI-assisted system design integration, covering the end-to-end workflow from requirements to subsystem design, to overall system synthesis. We start with the AI-driven requirement specification and data-driven exploration to understand the problem space. And I will show you the tool. I will soon show you the tool that we as a company use, and I use regularly, to design radar stuff on it. And this tool is a language model that we fine-tune to our purposes. And it has an input, for example, some books in this library that are radar books. As an example, we may want to maximize the area under the curve for key performance metric through this integrated design process. What I mean by that is, for example, I had a lecture, I think a few weeks ago, on the DSP pipeline involved from the road data through the detections coming out of the radar, which is XYZ, Doppler, and so on and so forth. Okay? These chain of signal processing algorithms are driven by, for example, the FFT algorithm, the windowing algorithm that is coming prior to the FFT, the CFAR, the constant false alarm rate detector that we do on the spectrum, on the output of this Fourier transform, FFT, and the criteria we use for reporting if it's a target or it's not a target, it's just noise. Okay, all of these sub modules inside the pipeline of the DSP, of the signal processing, are fed with hyperparameters, if you will. For example, the windowing function that we use prior to applying Fourier transform or FFT is variable. We can choose any windowing function that we want. We can even optimize for it using AI. We're doing that. Okay? How do we choose the windowing function that will maximize our detection capabilities? Okay. In the FFT, how do we use the FFT lens and some FFT tricks to maximize the detection capabilities? CFAR, how do we use the windowing, the guard interval, and the reference cells outside the guard interval for estimating the noise in order to maximize the detection performance? All of these questions can be answered using AI with an optimization problem, maximizing the area under the curve of the detector. Okay, so the goal is to leverage AI and data-driven techniques throughout the entire system design, and not only in the DSP chain, to design the life cycle for a radar with better or more efficient performance. Excuse me. Okay, let's dive into some aspects, some specifics. Antenna arrays. So antenna arrays are, it can't be re-emphasized. There are key technology for wireless communication, radars, and a lot of other applications. Optimizing the geometry and the weightings of the antenna elements is critical for achieving high performance radar. Beamforming techniques, like when we point the beam in the direction that we want, and we put a null in the direction of the interferer, is another important capability in radars, also communications. It's used in OFDM extensively, where the AI algorithm can dynamically suppress interference from jamming signals, for example. These advanced antenna array optimization techniques enabled by AI are essential for robust high-performance radars and wireless systems in general. Okay, so in terms of antenna array, I wanted to give some of the research that is done. There is a nice article, a very nice survey and article in IEEE Access. It's free. That is titled Applications of Machine Learning and Deep Learning in Antenna Design, Optimization, and Selection. And this is a review article. Another review article or a survey is this paper in Elsevier. Is going beyond RF, the survey of how AI-enabled multimodal beamforming will shape the next generation standards. And we can see inside, I put a picture of the references that they quote, of some of it. It's a lot more than this. And you can see a lot of references that are using AI, artificial neural networks, SVM algorithm, ANN, it's artificial neural networks, and MLPs, which is multi-layer perceptron, for the task of beamforming an antenna. So, and this is stuff that is not reserved only for the academia now. We use it with projects with our clients, and the industry uses it. For example, we can take this workflow, and we can see that it's a semi-AI aided workflow. So we start by designing the antenna design using a CAD or any other antenna design software. In this case, it's taken from this paper. So in this case, they used FECO. They observe simulated result after the simulation, and we integrate FECO using HyperStudy. HyperStudy is a package in which we can select the desired variable, for example, length, width, slot size to be optimized. And we also select output variables to maximize or minimize. For example, the gain, the VSWR, or the return loss. So in any case, we can optimize some cost function using AI. Okay, and then we choose the machine learning algorithms. They offer a bunch of them, including genetic algorithms, including GRSF, global response surface method, sequential quadratic programming, and so on and so forth. And if we get the desired input, we're happy. If we don't, we reiterate until we do. Okay, so this is an example for MATLAB. MATLAB is the main, MATLAB and Python, okay, are the main tools that we use for benchmarking radars, for simulations, and for evaluating and designing novel algorithms in the radar arena. You can use MATLAB for anything from waveform generation to design of antenna arrays and antennas, up to designing detectors, trackers, and object or target classifications. Okay, so the AI antenna object in MATLAB allows us to take a regular antenna from the antenna catalog of MATLAB and convert it into AI-based model. Now, all the examples I will share with you today are examples you can find online. Okay, there are open examples. Most of them are from MATLAB, MathWorks, and the reason for that is that I can't share specific customer examples because every customer has its own NDA with us, and we just can't share project details. Okay. Who can monitor, let's pause for a second. Who can monitor the chat to see if there are any questions? And Yves, can you do that?
Yeah, yes, we are monitoring the chat, no worries. If there are any questions that come up, we will...
Okay, great. Excellent, thank you. All right, so the AI antenna object allows us to model, take an antenna from the catalog and import it basically into an AI-based model. This AI antenna model can then be used for rapid characterization and simulation and design space exploration of the antenna. Using the AI model instead, at least in this first step, instead of a full wave solver, can significantly reduce the simulation time that is needed to fine-tune the antenna and meet our design goals. So here we show an example of an AI antenna object with an image of the antenna and some graphs that are optimization of the AI. The key benefit is being able to quickly explore and iterate over the design space of antenna and optimize the performance of an antenna through an efficient AI-based model. Another very novel work is the work titled "The Cognitive Radar Antenna Selection via Deep Learning." Okay, now make note that here I think it's Professor Yanina Eldar from Machon Weizmann, from the Weizmann Institute in Israel in the Rehovot, and so she's one of the authors of this paper. And how does it work? It involves selecting an antenna subarray from a larger M-element antenna array, and obviously there are, in terms of subarray of size K, there are M choose K possible choices, and they pose it as a classification problem that the AI or the convolutional neural network is solving. So there are limited amount of classes. Each subarray of these M choose K arrays, subarrays is a class, and the AI is choosing which class to trigger based on what criteria. They are minimizing what we call in the estimation theory the Kramer-Rao lower bound, which is to say they minimize the errors of the covariance matrix ability to infer and to localize target in space, or maximizing the SNR is the same. So this is a very novel network. We can see here that they are actually doing a very straightforward convolutional neural network that are most often designed for image classification, but they use it for designing or determining which subarrays in this large array of spots we can place an antenna to maximize or to minimize, in this case, to maximize the SNR or to minimize the Kramer-Rao lower bound. And that's a very nice and very novel approach, and people are using this already in the industry. Okay, waveform optimization. In radars, also in communication, we are employing waveforms. The waveform characteristics is what influences the reflected target power and our ability to estimate its location in 3D space and its velocity. So this is an exciting area where AI is exploring complex modulations or waveforms to improve radar performance. Adaptive processing using neural networks is enhancing techniques like the time-space or the space-time adaptive technique, the STAP algorithm, to better mitigate interference and clutter, as we will show in this presentation, as we dive into the tutorials. And these advancements in waveform design and adaptive processing are key to pushing the boundaries of what we can do with radars. And I think it will just get better throughout the next 5 to 10 years. Let's see an example. So here, this is, we will dive into a demo right after this slide. This demo is based on this paper, radar waveform synthesis using generative adversarial networks. And the idea is that, the idea in high level is that GANs, or generative adversarial networks, are based on a generator and a discriminator that are clashing with each other. The generator is fed, and the input to the generator is random noise, just random vector. Okay, the output of the generator is a waveform or an ambiguity map of the waveform. Usually, when you apply a noise into a system, into a black box, you get garbage in the outside, and that's exactly what the generator is producing in the early stages of the training. But as it clashes with the discriminator job, it's also a convolutional neural network. Its job is one and only, to say if the example that the generator made is a real waveform, or is it just a bunch of garbage, okay? And by relaying the feedback to the generator in terms of cost functions, we can refine the generator weights and train them to produce real waveform that will actually trick the discriminator to think it's real. Once we reach this stage, the training is done, and then the generator, by introducing just random vectors into it, you will get the output as a waveform, as a new waveform that you haven't seen before, so to speak. And this is exactly, by the way, how this, I think we all know the phase data set that GANs are like 3 or 4 years ago have revolutionized the computer vision industry with a fake, so to speak, but real looking faces and pictures of people. And this is exactly the same concept applied to radar. Let's go into MATLAB and see that in real, as a real example. Let me share the other window with you. Second.
Meantime, any questions?
Absolutely, yeah. If there is any questions, let me know.
Thank you. So thank you for interesting report. Sorry for my English. My name is Nir Regev. Could you tell could you tell us a little more about the genetic algorithms and use it and their optimization? Thank you.
Sure. Yeah, genetic algorithm. Now, I'm not an expert on this algorithm specifically, but genetic algorithm idea is to randomly create populations and subpopulations of the universe, so to speak, that by genetically changing some parameters in every subpopulation, you get a population that is refined, or a set of numbers, if you will, that are refined for a specific cost function that you want to minimize or maximize. Doesn't matter. So by employing genetic algorithm, you can search. It's basically a search over a multi-dimensional search space. It can be very high dimensional, actually, for a local or a minimum or maximum. Once you find this minimum, you have something that is more optimized than just random stuff. And that is used, that is what MATLAB used for finding antennas, for example, novel antennas and stuff like that. And this is also the tool that I showed before. This is what they use as one of the algorithms they offer that you can use to optimize antenna design. I hope this answered your question. Let me, so you can see my screen, right? Yes or no?
Yes, yes. It's,
okay.
Thank you for interesting. It's one question.
Sure.
I'm use genetic algorithm from optimization from agricultural, and I have a problem for many times. It's many parameters, and many times we need for the calculation.
Mm-hmm. Yeah, all of these optimization algorithms, whether it's genetic or gradient descent, they have their own drawbacks. And we need to carefully use them with regularizations a lot of times to produce the results that we want. And in AI and machine learning, there is a lot of artifacts that the algorithms and us using floating point numbers or even fixed point numbers in radar are producing that we need to take care of. And that's why they introduce heuristic methods, for example, like max pooling and all these kind of stuff in convolutional neural network to regularize and to make sure that the gradients or the optimization doesn't diverge. Gradient doesn't go to 0 or infinity, and so on and so forth. Especially with a lot of data, we use it in a batch manner, which means that you can think about it like we call it stochastic gradient descent. It's not really stochastic, but it's like iterating the gradient step, each step with another example of the data. And that causes a lot of artifacts in the optimization process that we need to handle. So all these algorithms are not perfect, but still we use them with some constraints in order to achieve the goal. Now, MATLAB, Python libraries, as well as this type of softwares, they designed these libraries with the levers that you can pull in order to make it converge. I hope this answered the question. So
thank
this
you.
is
Thank you. It's thank you.
But it's the same concept that you know from another industry. But only these days, back in 20 years ago, we called it optimization. These days, the industry call it AI algorithms. Okay, it's not to say that only optimization is AI, but an optimization is a subset of AI, I guess. Okay, so this is my website, by the way, and here I opened the page for this presentation, and we're going to go through the demonstrations or the tutorials, if you will. Here, all three tutorials that we have here in the top are taken directly for MATLAB 2024 examples. And again, I can't share specific customer architectures and implementations, but everything that I show you here today is something that we did, not specifically the thing that we did, but it's something that we did to customers around these topics and areas. And we do projects to customers in the industry, as you know. Okay, so let's start by we said generating novel new waveforms using AI. Let's go in. Okay. So this example will show us how to generate a novel phase-coded waveforms using deep learning network, and specifically the GAN concept, the generator discriminator network that we showed before, or generative adversarial network, whatever we want to call it. We will see the architecture soon. Okay, phase-coded waveforms. It's like in a communication, we change the phase of the waveform in a way that when the wave comes back to the receiver, we can correlate it or match filter it with a known set of waveforms, and then we get a peak where the target is, or the delay to the target, which is an indication of the range, right, in meters. Okay, so the times the travel, two times back and forth, the travel time is over 2 is the range to the object or to the target. And so by using coded waveforms, we get a nice cross correlation properties, like a very high main peak and very low sub lobes or side lobes, we call it. Okay, and the literature, including the research, I think the lifetime research of Nadav Levanon from the Tel Aviv University, are listing hundreds of these kind of waveforms. Okay, and I personally used a few in projects, obviously not all of them, but it's the same concept. They have good cross correlation properties. Okay, so let's see what we have here. The GAN is consisting of two networks that I already mentioned before. A generator that, given a vector of random values or random vectors, these are the inputs. Sometimes it's called latent inputs. These networks generate data with the same structure as the training data. It learns it learns the prior distribution or the PDF, the probability density function of the training data point. And once we have the probability density function estimated, we can draw samples out of it, and each sample in this case is a waveform. Okay. The discriminator is given data containing observation from both the training data, which is real data, real waveforms, and the garbage that initially is generated by the generator. This network attempts to classify the observation as true or generated false. And by quote unquote communicating this back to the generator, we can refine the weights in the generator to generate examples that the discriminator will fail to classify as fake. And once this is done, the generator is actually learned the PDF that we wanted to learn, and we can generate new stuff, new stuff that we haven't seen before. Ambiguity function of, it's an example, this is an example of an ambiguity function of the Frank phase-coded waveform of length of 64. And the ambiguity function is always plotted as a 2D array, or an image, if you will, without the color bar. I mean, the image is without the color bar. We use the color bar to see where we have the most gain and so on. And it's always in the delay. This is range in the x-axis, and Doppler in the y-axis. So we get a distribution of delay Doppler pairs, if you will, for each waveform. Again, we want this distribution to be like we call it sometimes, we call it a needle, and the rest like a Dirac delta. That's the ideal, okay? We never get it, but that's the ideal. Okay, how does it work? Again, the discriminator is fed by this image, which is real, and this image, which is generator generated, which is in the first stages of the training is just noise, it's garbage, okay? And the discriminator that is trained on the real images to say that it's real, immediately classify this kind of garbage as fake. Okay, the generator is generating fake signals. We calculate the ambiguity function, and this image is propagated through the networks. Okay. Again, the generator is generating a signal, not the ambiguity function. This ambiguity function generation is very deterministic. It's nothing probabilistic about it. It's just a short time Fourier transform of this time domain signal that the generator generates. Okay. Now we want to train again the generator to fool the discriminator, right? And train the discriminator to distinguish between training and garbage. So the next thing that we do, and you guys can run it in MATLAB as well, is downloading the data, and then we define some parameters of the radar, like the pulse repetition interval, the number of chips inside a pulse, or this is a parameter of the code, of the phase code, the sample rate, and so on and so forth. And we define the discriminator network. The discriminator network is defined here. It has the image input layers. The input again is the input here is the 2D ambiguity function map or image, and it's going through convolution, padding, ReLU is the nonlinearity, and then dropout of 30% to establish or to fight the vanishing gradient and to fight overfitting and stuff like that. And then it's another convolution layer, and then another one, and then another one. And finally, it's a fully connected layer. And that's it. That's the discriminator network. We do the same. This is how it looks like, by the way. MATLAB can plot it for you. You can see the first, second, third layer, and fourth layer. And then we flatten everything, and it's going to a fully connected layer, which is an MLP and multi-layer perception. And we define, by the same token, we define the generator network. The generator is generating a signal, the output is signal, and the L2 norm, or the minimum, the mean squared error, is used to minimize the square error of what is generated and the actual training example that is an actual signal, an actual waveform. Okay, we can see the plot of this network here. Here we have also convolutional neural network layers, ReLU, which is a nonlinearity, and so on and so forth. Okay, then we define the loss functions. We define everything that is used, in the loss function. The math is down there. We'll get to it, and then we started training. We defined all the training parameters, like the number of iterations for the generator, for the discriminator, the learning rate, and so on and so forth, the gradient decay factors. And we then plot after the training is done. Obviously, the reason I'm not doing it in MATLAB is because it will take forever and it will just consume the whole lecture, and even more. For example, this network was running 19 hours, 11 minutes, and 30 seconds. Okay, and we can see here 3 graphs. The loss is converging nicely to a constant that we cannot do better than it with the data that we have. Okay, and we see that there are 2 lines here. The discriminator with a gradient penalty, this line is converging faster, a little bit faster in the beginning, but they all converge to the same level. And this is the generator loss, the yellow one. Okay, and now we can use the generator. Once we're done with the training, we can use the generator to generate new samples or new waveforms. So this is the angle or the phase of the generated waveform. We plot the ambiguity function. We see that it looks kind of the same, but a little bit different from what we've seen before. We can plot the Doppler cuts. We can zoom in and see that it has a nice thumbtack at 0 delay, and some side lobes very much attenuated on the sides. And this is another waveform. You can see another waveform, another example, different from the other one. Again, this is the 0 delay cut, the 0 Doppler cut. And here we compare between a generated signal and a training signal. And we can see that they all, the training signal is actually achieving 5 dB more in peak to side lobe level. So the generator is generating nice waveforms, but it's a little bit higher in terms of side lobe, okay, which is not good. We can retrain it or add more data and examples if we want to further optimize it. Okay, and we can see here the 0 microsecond delay cut, and it's very well matching to the training signal. Now, a very important analysis here is what we call the correlation analysis. So here we are correlating the generated signals with the training signals, which are true signals, like codes that we know. Okay, we can ignore the diagonal because this is the signal compared to itself, okay, which is the correlation is always 1. The diagonal is meaningless. But we see that here in the sides we have generated, or here in the sides we have generated waveforms that completely are uncorrelated in terms of the Pearson correlation coefficient with waveforms that we know from the literature, which is to say that we succeeded in generating new, innovative, novel waveforms. And now we can take these waveforms, run it through the pipeline of the radar in simulation, or even in real. We can transmit these kind of waveforms and see how it behaves in real life. Okay, if you want to read more, the math is here and everything is here, but I'll skip that for this presentation. How much more time do I have, Yaniv?
45 minutes.
Okay, so I'll try to squeeze everything in here. Okay, so let's continue here. 1 second. Let me stop the sharing here. Let me do this, and then do this. Second. Okay. Share screen. Okay. Back to the presentation. So we covered this example. Okay, how does AI used in radar to enhance target tracking? When we design a tracker, we have multi-target tracking. When we have multiple targets flying around, so for example, we should track each and every target simultaneously. Okay, so when we have just one, it's an easy task. When we have many and we get returns from the radar, we have to associate what we get to a live track. This association is a classification problem that can be tackled with AI. Okay, this is one. The actual tracking filters, which is most oftenly, almost 99.999% of the time, is using Kalman filtering, and there is a work of one of the rising stars, I think, in the academia. Is also an individual from Israel called Guy Revach, which is this work is called Kalman Net, which is a data-driven Kalman filtering. And here he uses a neural network to assist with the tracking target type of applications. And there is some papers that he published about this during his master's and PhD, and I really like reading his texts. So this is target tracking. Let's continue. Okay, object classification. Okay, this is stuff that I've been using in radars and machine learning, AI, for decades. Okay, when we get a return from the target and we start tracking it through space, we want to know, for example, if it's an aircraft, a drone, or a bird, because we don't care about the birds, right? Sometimes they travel through space exactly like drones, but we don't care about them. How can we tell if it's a drone or a bird? That's where AI and advanced radar signal processing is coming into play. Another example is pedestrian bicyclist classification for autonomous vehicles. Okay, another is human pet classification for, not triggering an alarm when my dog is walking in the house. Another application, which is more rare, but still we did it for a company, Aleph Zero did it for a company, is human classification. So differentiating if I'm walking in front of the radar or Yaniv is walking in front of the radar. Say it's Yaniv and not Nir, and vice versa. Let's do a quick introduction into the microdoppler effect in radar. Microdoppler effect in radar is a phenomenon that refers to the modulation of the received signal due to or caused by the motion of small scatterers on the target. Examples: when I'm sitting here and the radar is reflected from my body, the heartbeat, that is a vibrating target, will modulate the returning wave. Also, my breathing will modulate the returning wave. For payloads from drones, will modulate the returning waves, and these kind wings flap in birds or human walking, the hands and the feet are modulating the returning wave. This is like in a few sentences what is the microdoppler phenomenon. It's a unique signature that the target is putting inside the time domain signal as well as the Doppler domain, which is the frequency domain. Let's see some examples. These are real stuff that we did in our projects. These I can share. And here you can see how I demonstrate. Let me fast forward here. Here I demonstrate, close this. Here I demonstrate, this is a camera tone or a fork, tuning fork. When you hit it, it vibrates in a certain frequency that is deterministic, like 150 hertz. Okay. I emit the radar wave on this camera tone, and it reflects back to the spectrum, or sorry, to the radar. And then we take out the spectrum. What we see here is a radar, a FMCW radar, working in 24 gigahertz. What we see down here is a graph that the x-axis of this graph is frequency or velocity, Doppler velocity. The y-axis of this graph is the time. So it's like a waterfall type of graph. Let's play it now. I didn't hit the camera tone yet. I'm going to hit it soon. Let me fast forward. Okay, so now I hit it once, now I hit it twice, and now I hit it the third time. And we can see very well the side lobes that we see on the spectrum. This is a unique signature of a vibrating target. The side lobe spacing, the spacing between the lobes, are exactly this 150 hertz of the tuning fork. Okay, so we can actually classify the vibration frequency from the spectrum. Now, if we use this as an image, as an input to a convolutional neural network, we can classify the targets with it. And we don't actually necessarily need to actually do it on the image. We can take the time domain signal and input it directly into a 1D convolutional neural networks. Another example is fall detection microdoppler. The waves that you see here are regular walks. My partner Ilya is walking on this treadmill, but this treadmill is a tricky treadmill because it moves, it gives you a jerk for initiating a fall. This is for elderly care, okay? This fall, obviously, is not gonna fall. He's trapped by this system of bells to the ceiling, but we can classify the actual start of the fall by using this type of treadmill. This is regular walk, and boom, once he almost fell, obviously, the instinct of the body is to try to balance and to get the center mass back in its place. So movement of hands and limbs in general are a part of a fall. And you can see here the movement of limbs, and AI can detect that, these anomalies or these events. Okay. Another one, and this is just for fun. This is stuff I like to experiment, and I took the fidget spinner of my son and I put it in front of the radar and span it, and you get this beautiful microdoppler signature. Obviously, it slows down in time, so this is why it's converging to 0. These are all side lobes. Actually, theoretically, it goes to infinity, but obviously it attenuates. It actually governs by the amplitude of the side lobe is actually governed by a Bessel function of the first kind, exactly like in FM modulation, if you are familiar with that. All right, so this is in terms of examples. Let's go. Second, let me. Okay, let's go back to the presentation. And this is AI system modeling and simulation. Okay, before we dive into that, I still want to go through. I have 15 more minutes, right, Yaniv?
35 minutes.
35 minutes. Great. Okay, great. So I don't have to rush so fast. Okay, so let's go back to MATLAB or to my website to see the examples of MATLAB, and we can go back to the presentation right after. Share screen. Oh, sorry, I'm back in the presentation. Okay. Share screen. Now we're back here. Let's refresh this page. Okay, so target classification here, example, and this is again example taken directly from MATLAB 2024 examples, and we classify between a pedestrian and a bicyclist on the road. The way that we do that is by simulating a pedestrian, a bicycle, and we are using the time frequency representation or the short time Fourier transform image as an input to a convolutional neural network. Okay, let's see it. So this is an example of a pedestrian. You can see the contribution from the leg, you can see the contribution from the arm, and you can see the bulk translation of the human walking. The bicyclist is kind of like a vibrating target in the frequency of the rotation of the wheels, which has a lot of side lobes very close to each other throughout the spectrum. And the car, in this case, a stopping car, is starting with a velocity, and actually it's an accelerating car, of let's say 100 and 500 hertz, which is a certain velocity, and up to 100, 600 hertz, which is an acceleration throughout this period of 2 seconds or 15 seconds. So these are examples of signatures, micro-Doppler signatures of pedestrian, bicyclists in a car. Now we will use the car to trick the neural network to give us, we call it car noise or car interference, to give us bad results, and we will see later. Okay, now we combine the objects. For example, this is a pedestrian and a bicyclist together, not in the same range, but together in terms of time frequency, frequency and time representation, the STFT representation. And we generate training data. We move the objects at different speeds, different ranges to the radar, different aspect angles. For example, for pedestrian, we can determine the height, the heading, and the speed. For the bicyclist, we can determine the heading, speed, transmission ratio of the gear, pedaling or coasting. This changes. If you also move and pedal, this changes the signature a bit. And for cars, we just randomly sample from the interval of between uniformly sample from 0 up to 10 meters per second in the X and Y axis. And the way that we do it is we generate the STFT, which is also called the spectrogram. We then scale it, and we normalize the amplitude to be between 0 and 1, so that the AI algorithm or the neural network can actually digest it properly. Because in terms of scaling, this can go from plus 40 dBs to minus 40 dBs. So the AI don't deal very well with high numbers. Okay, we download the data, which consists of not a lot of pedestrian actually and bicyclists. And these are not a lot of examples in terms of deep learning. And we then define the neural network architecture, convolution layer, again, another convolution layer, max pooling, and so on and so forth. It's a convolutional neural network. Okay, we can see the breakdown here. You can see the strides, the max pooling, the convolution kernel is 5 by 5, and so on and so forth. We use the Adam optimizer. We define the option for the optimizer, and then we train it. We can see that it converges to a very high accuracy and very low loss or cost. And then we generate what we call the confusion matrix, which is in a multi-class environment. We use this confusion matrix, and we want the numbers in the main diagonal to be all of it and the rest to be zeros. Okay, it's never like that, but that's what we want. That's 100% precision. And we can see here, for example, that the pedestrian, when presented with a one pedestrian example, 975 out of 1,000 example were classified correctly. 25 examples were wrongly classified as two pedestrians. Okay, and the rest for all the examples here, bicycle plus bicycles and so on and so forth. So this is how we treat multi-class. By the way, I have a lot of tutorials in my website, not necessarily for radar, also general and machine learning and AI stuff. And we use a lot of these confusion matrices. Classify with signature with car noise. Classification of signature with car noise is basically introducing a car into the signature and letting the neural network that is not trained on a car, only on pedestrian and bicycle, to still try to infer whether it is pedestrian or bicycle. Okay, we can see the results here. We can see that now the results are bad comparing to the result that we've gotten before. These outside the main diagonal of this matrix is heavily populated with wrong classification results. And now we are retraining the convolutional neural network from the point that we stopped. So it's like transfer learning. Okay? We're retraining it by adding to the examples that we show the neural network or the data, the car noise. Now we don't want the network to say if it's a bicycle, if it's a pedestrian, or if it's a car. We just want the neural network to be able to classify between a bicycle and a pedestrian when a car is present, or when car noise or interference is present. Again, we train it, and then we can observe the results. And it's a lot better than before. It's actually not bad at all. So this is target classification, and this kind of application we developed a lot in many industries and many type of applications. Okay, for running real time on a customer and either FPGA or CPU or GPU. Okay, the last example here that I want to cover real quick is the maritime clutter suppression with neural network. Okay, so the maritime clutter suppression is basically there is a radar on top of a vessel, a ship in the ocean. It scans the environment, and the waves of the ocean and the movement of the radar are causing a lot of clutter. We call it maritime clutter. And in this example, we use neural networks to suppress it almost completely. And let's just run through it pretty fast. These are the parameters of the radar, of the targets. These are the parameters of the wind speed, wind direction for the simulation purposes, heading and so on, target speeds and so on. We're preparing the data, we're generating the data, and then we define the architecture. First architecture is a neural network architecture that has in the last version, in the last layer of it, a comparison to the actual ground truth, no clutter type of image. And then it tries to minimize the error between the generated image from the neural network and the actual true image without clutter. And once the error is going down, this network is learning how to generate or to declutter images. The input to this network is a cluttered image. Okay, and we can see here all the layers. It's convolutional neural network basically, and we can see the training and validation are compared because we want them to be closely matching each other to reduce our risk of overfitting. And then we can see the results. Now, this is the typical image that you see in radars, in maritime radars. A lot of clutter, 2 targets here, and here is the decluttered output from the network, which is pretty awesome. This is great. And same here, same here. Okay, and there is another example here. There is another framework that we use more often than the other one, which is an autoencoder or I call it cross encoder or encoder decoder type architecture. The encoder will reduce the dimension of the input image into a vector, and then this vector will inflate into an output image. Okay, so input image reduced to a vector, inflating into an output image. The output image that we use to train are the ideal images. The input images are the cluttered images. And we can see here, let's just run through it quickly. We can see here that the network architecture is also convolutional encoder decoder architecture, but this time we start with the convolutional layer, and the decoder is a transposed convolutional layer that takes a vector and inflates it into an image, basically. And this, in this case, the radar image. And then we train the network. You can see the network training and validation. By the way, this jumping, this noise is because we're doing this, what we call the random gradient descent. And we can see something very interesting. This is the original image. This is the ideal response without any clutter or noise. And this is the decluttered image, which is amazing. And now we see that not only do we have clutter here, but also the clutter completely obscures this part of the target right here. This is the ideal response. And because it was trained on the ideal response, it can infer where the target is missing and utilize the training to cover where the target is missing. Same here, this is actually very highly cluttered, and it's almost completely removed. You can see here that, for example, in this case, where half of the target is missing, the neural network fails to infer everything else. It's a little bit here, but not more than that. But in this example, for example, when there is just a segment, a short segment missing, it does a very good job. Now here, that's the last one. Here, you can actually, it's hard even to see the target. Or is this the target, or is this the target, or is this the target? I don't know. The neural network was trained, and it does know how to infer the target and suppress all the surrounding clutter. Let's pause for questions. Do we have any questions?
Nir.
Yes, sir.
So when you apply here, like just like you showed, first of all, great lecture. It was very insightful, very interesting.
It's not over yet, but thank you.
Yeah,
thank
but
you.
I enjoyed it, and I enjoyed it very much. So thank you. Just wanted to ask, just as an example, like looking on these images, the operation of the decluttering, right? So eventually you take your trial network and you apply it on the original image. So I imagine it as like a sequential like convolution, right? Eventually, right? This is what's happening on the actual image. You have like different convolution kernels that happen like sequentially one after the other. So I'm interested in understanding like what happens like do you know what happens like to the noise in the image? Because like I see the pattern, but I also see that you have like distinct like different noise patterns in the image, right? Like if you have an original image that is very noisy, you will get a decluttered image that is also very noisy. And in your last image, you had like a very distinct noise pattern at the bottom of the image. So regularly when we're using like standard convolution kernels and standard filters like Kalman filter, we know in advance what to expect in terms of like the noise behavior, etc. So like what about like what about here?
So the architecture that we use here is a unique architecture that is borrowed. Since I've done a lot of projects also in computer vision, I know that this concept was in computer vision already 7 or 8 years ago. Okay, now what we do here is in specifically to denoise images, like natural images, okay? Not radar images, natural images. What it does, I mean, in neural networks, we don't really know what it does. We just have hints of what it does. So it's either representing the target distribution function, or it learns the noise distribution function to suppress it. And random noise cannot be completely suppressed, okay? It can only be smooth mathematically, okay? So this is what you see here. You see smooth portions of the noise. And it's very natural to see that, because we know that random noise cannot be completely suppressed, never. You can try to maximize the SNR, but you still have a signal to noise ratio that is not infinite.
Yeah, but here, for example, it's not a random noise. This is why I'm asking. It's
smooth. Yeah, it's smooth. It's very, very high correlated noise. It's like running a smoothing filter on noise in an image. You mentioned Kalman filter. It's exactly what Kalman filter is doing, right? Kalman filter learns the statistics of the noise, okay, the Q matrix and the R matrix, and it produces the best estimate for the signal, quote unquote, or the quantity that we want to estimate, or the state vector, according to a very well-known criteria, the minimum mean square error, or the Bayesian criteria, okay? Is there still noise in the smooth track? Of course there is noise. And this is the covariance matrix of the Kalman filter. It's never zero.
Okay, thank you.
Sure, absolutely. By the way, I developed a lot of trackers and Kalman filters in my, I'm still doing it. So yeah, feel free to ask about that as well. And to contact me afterwards as well. Yeah, go ahead. Another question?
To Kalman filter as well. So in a recent application I saw of a generative model, I saw something application.
I can't hear you very well, sorry. Can you repeat?
How about
now? I can't hear you at all. Oh, now I can hear. Now it's good.
Wait.
Loud and clear.
Okay, but my mic broke, so I'm gonna just hold it like this. I saw a recent application where somebody was using a large language model, sort of a large language model, to predict the next location of a moving target along a road. And that sounds pretty much like the application I would use for a Kalman filter. And I was wondering if we're not reinventing the wheel in many ways by trying to apply all these new methods to problems that we could easily solve with the good old methods, traditional methods that we used in the past.
Yes, completely in agreement with you. The way that we are tackling the tracking problem nowadays is with the tracking filter, I would say, is with the good old Kalman filter always in radar, okay? I don't think there is a company that I know of, and I worked with a lot, that will replace the iterative, very lean implementation of this Kalman filter with a bombastic, bloated model of AI. Okay, what the example I'm showing here is not about Kalman filtering at all. It's about clearing the images of radars from noise. And this is not tracking anything here. Okay, this is just saying this is the image so the operator can look at a brighter image, so to speak, and spot a target. And again, a lot of this stuff is not yet implemented in radar. And we'll, in the next slides of the presentation, actually discuss that. In terms of tracking, I would say 100% no. But tracking filters are not only smoothing, like the Kalman filter is just a part of the tracking filter. Actually, the main problem of a tracking filter, outside the smoothing and the Kalman filtering, is the target to track association problem, in which when we have a lot of tracks going around and a lot of detections that are coming from the radar, we need to decide which detection to assign to which track. Currently, we are tackling these problems from, as far as I can tell, in my 26 years of industry experience up to today with probabilistic methods. But AI, or specifically convolutional neural network that are lean, 100% can solve this association problem or classification problem better than any method that we invent. And there are drawbacks. We will touch that soon. But still inside the tracker, we can still utilize AI specifically for targeted track association or plotted track association, sometimes it's called, or detection to track association, which is a classification problem. Okay, let's go. Let's go to this. In terms of system design, there are some considerations and proposed solutions for best practice of AI inside system design of radars. For example, memory. AI models, especially deep learning networks, require significant memory, right? Storing weights and activations and so on and so forth. High resolution radar data is also high on memory. Together, they demand even more high memory, even higher memory. The proposed solution is to employ model compression techniques, such as pruning models and quantization of the weights and the quantization of the numbers inside the model to reduce the memory footprint. And we have done some very nice projects to customers in which we've done model pruning and quantization of model to run on fixed point. And this brings us to the discretization of neural networks, which is basically the training. You can take measures in the training, we call it quantization aware training techniques, to optimize AI models for fixed point arithmetic, and to optimize then to optimize everything inside the pipe of this or the graph of this neural network. Usually it's very lean, okay, in these kind of applications, as it has to also adhere to latencies. Okay, so this is the proposed solution, apply quantization aware networks, the bit depth. Okay, almost all radar systems that I worked on, barring a few examples that I can count on my hand, are using FPGA straight from the get-go. And over there, you have to be very careful about bit depth, about bit representation, fixed point representation, and the implementation of all the algorithms from windowing to FFTs to detecting, in terms of the requirements for the fixed point implementation. And the presentation of neural network, or even a simple machine learning algorithm, AI algorithm, will involve further optimization of bit depth, okay? And we have ways to deal with that, like mixture of bit depth configurations and stuff like that. Computational load. This is a high, usually AI algorithms are high in computational load, and we in radars, we want to simplify the hell out of our computations because we just don't have the resources to do it in a certain latency in real time. That's why we use the Kalman filter, and we like it so much because it's iterative and we don't have to store anything other than the last example and last sample in memory and so on and so forth. It's very lean, but computation load of AI algorithm are heavy. So what we've done is taken them to be accelerated in FPGAs and sometimes even CPUs or GPUs. I know that my company, not me specifically, I was also designed some ASIC cores to deal with that. This is my partner's expertise guy. He's also my brother. Latencies, again, we mentioned latencies, and we can employ model distillation techniques to create lighter and faster AI models. We've done that as well. Power consumption, also a very, I guess it's a crucial, it's a seminal metric in system design that we have to handle very carefully, because these models, if you inflate them, they will heat up the apparatus and consume a lot of power. And we have to be very careful in the models. We have to improve them. We have to make them lean. We have to prune them. and so on and so forth to basically consume less power. And there are obviously more than just 7 examples. I chose to talk about these 7 examples. Let me go back to the presentation. I never got to do something very important that I will show you right now. Okay. Yeah, go ahead.
Is the link to the website or the paper that you're showing now in the chat?
Yeah, absolutely. Here. AI in radar. This is the chat. This is the link. It's open to you guys. It's not on the main website menu because it's for this lecture specifically, so only you can access it. Everyone with the link can access it, but I'm going to make it available for you in the coming days, and then, just to ruin my website, I'm going to take it off. But you can always reach out to me, and I will give it to you very gladly. I have it on the document. Okay, so let's go back for a second to the presentation, and then jump back to another very nice demonstration I'm going to show you.
Just in favor of time, we have 9 minutes.
Okay, you know what? So okay, I need 4 more minutes, and then we can have 5 minutes for questions. Is that okay? Thank you. Okay, so I'm going back to the screen sharing. Let me show you what I use for radars design. Okay, so this is an example of a think of it as a ChatGPT, okay, but it is fine-tuned and specifically tailored for dealing with the lecture notes that I give it, the books that I give it, and AI and radar knowledge that we basically train it on, okay, or fine-tune it on. So let's do this example for the next 3 minutes. I want to build a radar that can detect drones of RCS radar cross-section of 1/100 meters squared from 500 meters maximum range. Please suggest a radar system architecture, explain all your assumptions and suggestions, and give a Python code when necessary. And we can go here, and it's going radar type, operating frequency, transmit power that we need, antenna design, signal processing, assumptions, and it's going with all the calculation needed, like the radar equation, the type of gains that we will use and need from the antennas to achieve that, and a Python code. Let's quickly go into the Spider here and run this Python code. Let me delete everything here, and we can see that this Python code that was generated by my AI is saying that the required transmit power for detecting a small drone in 500 meters is 31.39 dBm. Okay, now I go back to here, and I told him, take the 31.39 dBm and produce a Python plot to that is received power versus range. Okay, I want to know how I do in terms of range, and it gives me this code. If we go to this Python, it generates this graph for us. You can see that it's -100 dBm, which is the sensitivity of this specific radar, minimum detectable power in 500, and we're doing pretty good in 100, 150. Okay, so we can evaluate stuff from these code snippets that it generates for me, and I use it daily with customers' project, and then suggest suitable antenna architecture, again, justify assumptions and so on. And so it goes. We want to use AESA, which is what I would choose for this. I built already AESA's radars before. What band, X band or KU band, which is also intuitively correct. Antenna design, rugged and compact, and so on and so forth. And it gives you a conclusion, and I can reiterate and have him produce more data for me and more stuff for me and more equations, and I can copy this. And actually, I already asked him to give me a draft for a specification, for example. Okay, now this is the last example I'm showing here in this presentation. I want to go back just to the presentation part and conclude this presentation. With your permission, let me share my screen again. Share screen, where is it? Zoom. Okay, share screen. This is it. Okay, so let's fast forward here. Second. Okay, let's fast forward in the slides here. This is actually very close to the end already. I have some more slides here, but you can read it after the fact. I talk about cognitive radar and multifunction and federated type of AI. And then we'll get into the concluding slide. Okay, there it is. One second, what is this? Okay, yeah, so I want to conclude this presentation. System design consideration and in AI, this is the link that I posted in the chat if you want to revisit it. So this is just a summary of what we did here. And the last presentation here is, I just want to thank you all for your time and attention today. I hope this information was valuable and that you enjoyed this presentation. As you can see, the best way to reach me is through my email. It's contact@drnirregev.com. I'm always very happy to answer any questions or schedule a meeting. You can schedule a meeting with me directly on the website. It has a calendar gadget, a widget there. Just use it if you want to schedule with me. And this time, just, I'm happy to take questions. Feel free to ask any question you want.
So Nir, thank you again. Like the last gadget that you showed, the AI system engineer, it's something that you trained?
Mm-hmm.
So
let's say fine-tuned.
So it's like you took a standard LLM model and you fine-tune it on, okay. And the input is something that you wrote, or like you input it there? Just from curiosity, I don't know, like a rather textbook or what?
Textbooks and stuff that I wrote, yes.
Okay.
Textbooks, papers, not only radar, also AI, because it's I want it to be a combination of it.
Okay, and this is like, this procedure is something that takes a lot of time, or is it limited by the amount of data you can add? Can you say something more like technical about this procedure if I want to do it in my organization, for example?
It takes, we are doing it for customers, but it takes a good few months to do it, and it's there is almost no limit to the amount of data you can generate. It's just a matter of utilizing a proper database for it, so that the AI engine can refer to. That's about it.
And it's text only, right?
Yes, it's text only. Yeah,
okay.
Text only.
Okay.
Yeah. But it can generate math for LaTeX, and it can generate code, as you see, also in MATLAB.
But it understands as input only text.
It understands as input. No, okay. We can do something that is taking images and PDFs also as inputs. It's easy, and these PDFs can contain images. So as inputs, no, but as output, it will not give you. For now, these models are not capable of giving you a proper representation, for example, of a block diagram. Okay. It can describe it in text, but it will not draw it for you.
Okay, thank you.
That's what I mean. Sure, absolutely. And obviously, this is an example. You don't have to implement it for radar. You can implement it for other interesting stuff. All right, thank you so much, guys. תודה רבה לכולם. I appreciate your time.
אין לנו עוד שאלות? אוקיי.
תודה רבה.
המון תודה, ניר. אנחנו מאוד שמחים גם השקעת מזמנך, ואתה עכשיו כבר ממש 12 בלילה אצלך, זה כבר מחר, רשמית.
בדיוק 12, כן.
עכשיו אתה באותה יממה שבה אנחנו נמצאים, זהו.
אתה מבין איזה יופי? אני מרגיש יותר
אנחנו
קרוב.
מאוד שמחים, ורשמו לך פה גם תודה, גם על הסולידריות שכל כך נצרכת בימים אלה, אז באמת באמת תודה. וזהו, אני מניח שאם יהיו עוד שאלות, אז אנשים מוזמנים לפנות אליך וליצור איתך קשר ישירות.
כן, תרגישו חופשי.
אולי אפילו ייתנו לך סיבה טובה לבוא לבקר.
כן, אבסולוטלי. הלוואי, רציתי להגיד שני דברים. אחד, יש לי קומיוניטי בסלאק ל-industry veterans and people, like, אנשים עם ניסיון בתעשייה. אנחנו discussing new papers שם, וכל מיני דברים כאלה שקשורים ל-AI, לא ספציפיקלי לרדאר. זה אחד. אם אתם רוצים תפנו אליי, אני אכניס אתכם לשם. 2, אני מחפש מנטורים עם הרבה ניסיון בתעשייה לקהילה של סטודנטים. יש כבר יותר מ100 סטודנטים בקהילה, ואני הקמתי אותה רק לפני שבוע וחצי, שבועיים. זה בדיסקורד סרבר, וזה, מה שאני רוצה לעשות זה לעזור לסטודנטים, כל סטודנט יכול להצטרף, גם בישראל, ולעזור לסטודנטים להיכנס לתעשייה smoothly ו-seamlessly, אבל אני לא יכול לעשות את זה לבד. אז יש שם כבר גייסתי איזה 5 מנטורים, אבל כל מי שרוצה, מה שנקרא to give back, מוזמן להצטרף לזה, contact me, ואני אצטרף אתכם גם לזה. זהו, זה השני הדברים האחרונים שרציתי להגיד.
תודה רבה.
תודה רבה.
לזמן. ניר, המון המון תודה, ואנחנו כמובן נשמור איתך על קשר.